I welcome you all in this module of the course Modeling and Simulation of Dynamic System. Today we will be talking about the modeling of pneumatic systems. Okay. Pneumatic systems are very popular system in industry as they are compliant in nature, light in weight. Okay. So, because of this characteristic they are very much preferred, although they are not very accurate. These pneumatic systems differs from liquid in the sense that with pressure the volume changes and hence the density changes. If you remember in our previous lecture, we considered the hydraulic system and there we assumed the density of the liquid to be constant. Okay. But in pneumatic system we assume that density varies. As with other system models such as mechanical, electrical or hydraulic, here also we have the three basic building blocks and these are the pneumatic resistance, pneumatic capacitance and the pneumatic inertance. So, initially we will be looking at the definition of all these three building blocks, their governing equations, and then we will take up an example of the pneumatic system, which I am going to take here the case of a blower, okay, and we will try to model that blower. So, let us begin with the basics models, basic building blocks. First we take the pneumatic resistance. The pneumatic resistance is defined as the P1 minus P2 is equal to R dm by dt, where this dm by dt is the mass flow rate. Okay. Here as I said m derivative or m dot is the mass rate of flow and P1 minus P2 is the pressure difference or the pressure drop. Okay. And here R is the pneumatic resistance. Now, if you look at this equation is very much similar to what we have for electrical resistance, that is V is equal to I into R. Okay. So, what does this means that the V corresponds to the V voltage of electrical system corresponds to the pressure drop in the pneumatic system. The current in electrical system corresponds to the mass rate of flow in the pneumatic system, and of course, the electrical resistance in the electrical system corresponds to here the pneumatic resistance in the pneumatic system. Okay. So, this way we describe the pneumatic resistance with the help of this relationship, that is P1 minus P2 is equal to R m dot or m derivative. Next basic building block is pneumatic capacitance. Okay. Now, pneumatic capacitance is due to the compressibility of the gases, okay, and this is comparable to the compression of spring which stores energy in a mechanical system. Now, let there be a container of say volume B and say there is a mass flow rate entering to the container, and let this will be m1 derivative, and the mass flow rate leaving the container be say m2 derivative. Then the rate of change of mass in the container is going to be m1 derivative minus m2 derivative. Now, as I said there is going to be the variation in the density here in case of pneumatic system. So, if the gas in the container has a density rho, the rate of change of mass in the container we can give as m1 dot minus m2 dot is equal to d by dt of rho v. Okay. Now, here you can see that rho has got the unit of kg per meter cube and V has got the unit of meter cube per second. Okay. So, we have the unit as the kg per second. Now, here as I said, rho and V both are variable. So, when we differentiate here, we carry out the differentiation by part. So, we have rho dV by dt plus V d rho by dt. Okay. Now, this dV by dt I write using chain rule as dV by dP into dP by dt plus of course, I have V d rho by dt. Now, for an ideal gas, we know the gas law, that is PV is equal to mRT. So, from here I can define P as m by V into RT, or this is rho RT, or from here I can write rho as P by RT. Okay. So, from here I can define d rho by dt, okay, is equal to 1 by RT into dP by dt. So, basically I am trying to define this term here in this equation. Okay. Now, let us substitute for this d rho by dt in this term. What we get is m1 minus m1 dot minus m2 dot is equal to d by dt of rho v, and this is rho dV by dt plus V d rho by dt is equal to rho dV by dP plus dP by dt plus V d rho by dt, as I said, and this is what we got in the previous slide. And if we substitute this d rho by dt here, this is what we get. Okay. So, I substitute for d rho by dt as 1 by RT dP by dt here. So, what I have V by RT dP by dt, and if I take this dP by dt outside, this is what I get, rho dV by dP plus V by RT. Now, you can see that here we have the two terms are available. Okay. So, the pneumatic capacitance due to change in volume of the container can be defined here as C1 is equal to rho dV by dP. Okay. Similarly, the pneumatic capacitance due to the compression of the gas, okay, this is defined by V by RT. Okay. So, here in case of pneumatic system, okay, the capacitance is due to the change in volume of the container as well as due to the compressibility of the gas. Okay. So, for both we are going to have a capacitance, okay, and the total capacitance of the pneumatic system is going to be summation of these C1 and C2 here. Okay. So, let us substitute that. So, if I do that, this is what I get C1 plus C2 dP by dt, or I can write in terms of P1 minus P2, that is if I integrate this equation, this is what I get 1 by C1 plus C2 integral of m1 dot minus m2 dot dt. Fine. Now, if I recall for a capacitor, okay, for a capacitor we had C is equal to Q by V, where Q is charge and the V is the voltage across the plates, okay, and Q I can write in terms of current, that is integral of I dt. Now, if I compare this expression with this one, then you can see that this capacitance or the term associated with the capacitance in the capacitor is this term, that is 1 C1 plus C2. So, for a pneumatic system, C1 plus C2 tells you the pneumatic capacitance, okay, and these things I have already explained to you, that the pressure drop is basically equivalent to the voltage in an electrical system, and the mass flow rate corresponds to the current in the electrical system. Okay. So, this is about the pneumatic capacitance. Now, we will look at the pneumatic inertance. It is due to the pressure drop necessary to accelerate a block of the gas. Okay. Now, we have a block of the gas. Now, for this block of the gas, how much pressure drop is necessary to accelerate that? If we look at it, we can get the definition of the pneumatic inertance. Okay. And to arrive at, let us look at the Newton's second law, that is F is equal to mass into acceleration, or this is d by dt of mv, that is rate of change of momentum. Now this F which I am talking about, this F is actually provided because of the pressure drop. Okay. So this force is provided by the pressure difference. Okay. And if A is the cross sectional area of the block being accelerated, okay, that is if I have got a say block here like this is my block. Okay, say pressure is here P1 and say this here pressure is P2, and this cross sectional area is basically A. Then my expression is going to be equal to this P1 minus P2 into A. So this is the force and this is d by dt of mv. Okay. Now what I do, this mv actually I write as, this is basically momentum. So I write in terms of density and rate of flow. So rho into LA, LA is basically the length of this and A is this cross sectional area. So it is this L. So basically LA will give you the volume here. Okay, and this volume being multiplied by the density will be giving you the mass. Okay, and here this is your meter cube per second and divided by meter square. So that will be giving you meter per second. So basically here we get the momentum. All right, and this I can write, this A gets cancelled. So I have rho L Q. Now I can substitute this in this expression. So what I have, P1 minus P2 into A is equal to d of rho L Q upon dt. I can take L which is a constant outside. So L is outside. So I have d of rho Q upon dt, and this rho Q, if you look at the units here, rho is kg per meter cube and this is meter cube per second. So basically what we get kg per second. Okay. So this is d of m dot by dt. All right. So from here I can write P1 minus P2 is equal to L by A dm dot by dt, or if I write this L by A as I, okay, which I define as the inertance, then I get the definition of the pneumatic inertance here. Okay. I can simply compare this with an electrical inductance. Here you see, for electrical inductance we write the expression as V is equal to L di by dt. So here you see V corresponds to the pressure drop and I corresponds to the m dot here. Okay. So L corresponds to the I. So this is how we define the pneumatic inertance. So we have defined the pneumatic resistance, we have defined the pneumatic capacitance, and we have defined the pneumatic inertance. And now let us use these three basic building blocks to model a pneumatic system. Okay. So this is what next we take example of a pneumatic system. Let us take a bellow. Okay. So I will explain you about a bellow. Suppose this is your bellow here, and in this bellow there is some constriction here, okay, which essentially provides a pneumatic resistance. Alright. So the constriction here that provides pneumatic resistance. Suppose the pressure drop here is P1 before the constriction, and after the constriction say the pressure is P2, okay, and say the area of cross section of the bellow is A and the displacement in the bellow is there X. Okay. Now as I said, the resistance is provided by the constriction which restricts the rate of flow into the bellow, okay, and the capacitance is provided by the bellow itself. Alright, and we can neglect the inertance here in this case by assuming that the flow rate changes very slowly. Okay. So we can assume that the acceleration of the gas is very acceleration of the gas is not there, okay, or that is 0. So, we can neglect the inertance and we can just use the capacitance and the resistance building block to draw the system equation for this bellow, okay. And this is how we are going to get the ultimate equation, but I will explain how do we get this. So, here you can see that this expression which you are getting here, P1 is the input pressure from here, that is the pressure as with say the gas enters the bellow, and of course, here the output say is the displacement x, okay, of the bellow. So, here you can see that this is a first order differential equation for the bellow. Now, let us see how do we get this differential equation, okay. So, our ultimate aim is here is to know that if my input supply pressure is P1, then what my displacement is going to be, or how my displacement is going to change with time for the given input pressure P1. So, let us begin with first of all we say model for the constriction here, alright. So, the constriction can be modeled just like a resistance, okay, in an electrical circuit. So, here the pressure drop P1 minus P2 will be equal to R into m dot, okay. So, this is the mass flow rate into the bellow is given by this one, as I said it is very similar to V is equal to Ri, okay. So, here this is the P1 pressure, this is the constriction and this is the pressure P2 and the mass m dot is flowing from here. So, we have this relationship where this R is the pneumatic resistance, okay, due to the constriction here, fine. So, as I said here pressure P1 is the pressure before the constriction and P2 is the pressure after the constriction, okay, or we can say that the P2 is also the pressure inside the bellow and R is the pneumatic resistance, okay. So, what we did, we define here for this case the pneumatic resistance, okay, and then next we will be defining the pneumatic capacitance. I have already said to you that we are not going to consider the pneumatic inertance, and then we will combine the relationship of the pneumatic resistance and the pneumatic capacitance, okay, in order to get the system equation. Now, as we have seen, all the, in this case all the gas that flows into the bellow remains in the bellow, okay, because there is no way for gas to escape out of the bellow, okay. Thus, the capacitance of the bellow is given by, this is the relationship which we have seen for the capacitance of a say pneumatic system, or this is the basic building block, the pneumatic capacitance building block definition which we have got, m1 dot minus m2 dot is equal to C1 plus C2 dP2 by dt. Now, as I said, there is no gas which is going to escape from the bellow. So, what we can do that we can take this m2 dot equal to 0, okay. Now, if I take this m2 dot equal to 0, this is what I get, m1 dot is equal to C1 plus C2 into dP2 upon dt. Now, why I am taking dP2? Because this P2 is the pressure here inside the chamber, inside the bellow, okay. So, we have m1 dot is equal to C1 plus C2 dP2 by dt, and as I said the from the definition of the constriction resistance here P1 minus P2 is equal to R m1 dot. Now, this is the expression which comes from the definition of the constriction resistance or pneumatic resistance, and this is the definition which comes from the pneumatic capacitance. Now, let us combine these two equations. So, how do we combine? I substitute for m1 dot from this equation into this one, okay. So, if I do that, what I get? P1 minus P2 by R is equal to C1 plus C2 dP2 upon dt. Alright, or I can write this as R C1 plus C2 dP2 upon dt plus P2 is equal to P1. So, here in this equation you see the input is my P1, the input pressure is P1, okay, and my output pressure is P2, okay, and this expression these are related by, as I said, this is the first order differential equation, and of course we have the terms which tells us the pneumatic resistance as well as the pneumatic capacitance, okay, and this shows how P2 varies with time for a given input pressure P1. But as I said, our interest is to know that actually how much bellow moves, okay, because of this pressure P1. So, that we can find out how much bellow moves because of this pressure P1. So, next let us see that how much bellow moves. So, to do that, let us assume that the bellow behaves as a spring, okay, that is it expands or contracts as a result of pressure change inside it. So, the bellow behavior I am modeling as a spring, the mechanical behavior of the bellow I am modeling as a spring. So, I am writing say F is equal to Kx, where x is the displacement of the bellow and K is the stiffness of the bellow, okay, and F is the force considering expansion or contraction, and of course this depends on the P2, because P2 is responsible for the expansion or contraction of the bellow, okay, and as I said K is the spring constant of the bellow and x is the displacement of bellow, fine. Now, but this F is equal to P2 into A, where A is the area of cross section of the bellow, okay. So, let us substitute that. So, we have the P2A, this is the force and this is equal to Kx. So, from here I get P2 as Kx upon A, okay, and this was my basic equation, the dynamic equation for the bellow, okay, and now in this expression I substitute for P2 is equal to Kx by A. So, this is what I get, R C1 plus C2 K by A dx by dt plus Kx by A is equal to P1. So, this is the same equation which I discussed in the beginning for the bellow. Now, here you can see that the input is P1 and the output is the X, and this is the first order differential equation which explains how the extension of bellow takes place, extension or contraction of the bellow changes with time when there is an input pressure P1, okay. Now, the question is how to evaluate this C1 and C2, okay. So, let us see how can we evaluate this C1 and C2. So, evaluation of C1 and C2. So, I can think of evaluating at C1, that is the pneumatic capacitance due to change in the volume of the container, okay. Here in this case we are talking about say bellow, okay. So, C1 I define as rho dV by dP2, it is actually rho dV by dP, but here the P is basically the P2, alright. So, but V is equal to Ax, so I put it here C1 is rho A dx upon dP2, or for bellow we have also seen P2A is equal to Kx, that is the force is equal to the stiffness constant for bellow and the displacement of the bellow. So, from here I get P2 as Kx by A, and if I substitute here for P2, this is what I get, rho A square upon K, okay. So, this is the pneumatic capacitance due to change in volume of the container. Next, the pneumatic capacitance due to the compressibility of the air, okay. So, from here C2 we can define as V by RT, and this volume I can take as Ax and divided by RT. So, this way I can evaluate the value of C2. Okay. So, we can summarize the basic building block definitions. Say inertance, electrical system, we have V is equal to L di by dt. So, here we have P1 minus P2 is equal to I dm dot by dt. Capacitance, V is equal to 1 by C integral I dt. So, here we have P1 minus P2 is equal to half C1 plus C2 integral M1 dot minus M2 dot dt. And resistance, V is equal to Ri. So, here we have P1 minus P2 is equal to R m dot. And energy stored or power dissipated, you know that in case of inertance and capacitance the energy is being stored, and in case of resistance the power is being dissipated. Okay. So, for inertance we can just write as half Li square as for the electrical system. So, here L in place of L I have I, and in place of capital I, and in place of current I have m dot. So, this is half I m dot square. For capacitance this is half CV square. Okay. For a capacitor the energy stored in capacitor is half CV square. So, here this is half C, where this C is basically C1 plus C2, okay, into P1 minus P2 whole square. And for resistance the power dissipated is V square by R 2R, V square by 2R. So, here it is 1 by 2 P1 minus P2 whole square by R. Okay. Now, using this concept you can think of modeling say pneumatic actuated manipulators. Okay. So, this is the image of Robotino XT, where basically there are 6 tubes here basically okay, which are pneumatically actuated. Okay. So, you can think of modeling of these each segment of the tube using the 2 basic building blocks which we have used for modeling of the bellow. Okay. So, those concepts can be used for modeling of these 6 tubes connected here, and of course, from there you can try to find out the tip position of the this pneumatic manipulator. Okay. Not only this, we can think of modeling of the elephant trunk, okay, or elephant trunk like structure say like this, again which is pneumatically actuated. Okay. So, this I am not describing in detail, it is just a thought for you to think about that how can we model this type of system using these basic building blocks. This is the reference, you can refer a very popular book by Professor Bolton, Mechatronics, Pearson, if you want to read it further. Thank you.